The following presentation was made by John Frensley at World's Finest Physics.
Time to torque. Torque? What did I say? Torque, not twerk. We will not be defying physics with dance moves. Instead, we're going to figure out how is equilibrium achieved as it relates to objects that are rotating. In this lesson, we're going to be able to define torque and calculate the torque that a force produces. We're going to be able to state the conditions for static equilibrium and write equations based on equilibrium conditions. We're going to be able to use equilibrium conditions and equations to predict what will happen. First, some vocabulary that we need to know. Torque. Maybe you've heard this before in your life. You need to apply a torque to something. If you're building anything or adjusting anything, you've surely heard it in YouTube videos that you've watched or read it in the instructions. Typically, when you're putting something together, you need to tighten the bolts of whatever it is you're putting together. And for this, there's a special tool called the torque wrench. And that torque wrench is set up so that way when you are applying a force, the amount of force that's being acted on the screw is accounted for, and there's a gauge on there to tell you exactly how many foot-pounds you're putting on it. Obviously, we're not going to be dealing with torque in foot-pounds because that's not useful to us in science. The symbol that we will use for torque is not the letter T. It is the tau symbol, the lowercase Greek letter tau. The units are newtons times a meter. Remember what I just told you? Foot-pounds. Foot is the length. Pounds is the unit for weight. That's what we use in America. Foot-pounds. But instead, it's a Newton meter in science and everywhere else around the world. Basic equations. I gave these to you in the last sneak peek video. That is tau equals R times F times sine theta, or torque equals R, which is perpendicular to F, and tau equals R times F, that is perpendicular to R. We'll talk more about that. Static equilibrium condition where none of the object's motions change. So that can be translational or rotational. We have radius vector, a vector that points from the axis of rotation to where a force is applied. That's the R in that last equation. Line of action, the infinitely long line that a force acts along. A lever arm or a lever arm or radius of action, the distance between the axis of rotation and the line of action, measured perpendicular to the line of action. What? It'll make more sense by the time you get to the end. I hope. It will.